welcome to the workshop of Imaris. This is going to be the basic and advanced level workshop. So how many of you have already used Imaris before? Never. You have used it, but just basic level. Right, okay. Okay, so it was, I would say it's the basic level, right? Okay. So, I mean, it was made for the basic and advanced level both, but we will focus more time on now basic level, okay? And how much we progress then and how much time remain, we'll go for the advanced level, okay? So Imaris, before we start with Imaris, this is the whole idea of image analysis, right? This is the software which works for image analysis and image visualization, okay? So if you see an image has a lot of information. It's a plethora of information. And what kind of information we can extract as far as image is concerned is that we have morphology. Maybe we are interested in behavior of the images, like different organelles of the cell, for example, and also their relationships with each other, right? So all this information is embedded in the image, and Imaris will help you to extract this information on different levels, okay? Right. But in today's scenario, we don't have only one replicate, right? We don't have only one image. We deal with many replicates, many conditions, many assays, different conditions, and stuff like that. So we have basically number of images. So Imaris also help you to organize your data. Like unlike Fiji, for example, you just have to drag and drop like every time you have to process one image. But here you can organize it so that if you publish a paper with the results, that data set is still there. So you can always come back and see what was your result from which you have extracted the result. Okay, so basically organization about the data. So the whole concept of Imaris is that we have data organization. Okay, so that is done by Arena module of the Imaris. Then we can pre-process or segmentation. That's basically the main focus of Imaris, that we can segment the data. Then we can write our different protocols, right, for the segmentations. It allows you to extract features, different varieties of features based on shape, morphology, intensity, which we're going to see now. And not only the features that like from image to numbers, but it also gives you kind of a statistical views of the data. So it also gives you a plots, right? This is also one of the feature that they have added in 9.0 version of Imaris. That is called as a vantage plot. We can also record videos. We can make an animation. We can make a snapshot for your publication. We can have a scale bar and all kind of things what you need. And of course, it supports all kind of metadata, vendor specific data, all kind of microscopy file format it can read. Okay, and most importantly, it supports Fiji. So as long as your image is readable by Fiji, you can actually read in Imaris. Okay, which we're going to see that case study one. Okay, so as far as the modules are concerned, and as far as DanStem is concerned, we have, are you from DanStem, all of you? Okay, so in DanStem we have both versions. One is a filament version and cell module. So I'll show you what does that mean. But we have Imaris core module, okay, which has a database basically here. We have a measurement pro, meaning that you can manually measure in 3D. What is it? Let's say, for example, you are interested in measuring the length, right? Orientation and things like that. You can do that. We have that module. We have a tracking module, so we can actually track the cells. We can have a co-localization, so we have a co-localization module also. We have Vantage, and also we have in one of the workstation we have a filament tracer, okay, and in one of the workstation also we have a cell. So, and we have XT means let's say, for example, Imaris can't provide you everything what you need, so there is a possibility of writing your script in Fiji or in MATLAB. So you have to come to me if you think that your requirement is not satisfied by Imaris. Okay. And batch module we don't have in DanStem. Okay. The reason we did not purchase batch module for the DanStem is basically we do not deal with many data, right? I mean, we have a huge data, but that's just one, like just handful of the images, right? Because we have mostly embryos things. So batch is not required so far. Okay, maybe in future, but so far we don't have batch processing, meaning that you just apply one algorithm for many images. Yeah. So don't worry about that. I mean, that's not a problem. Okay, As far as the supports are concerned, so Imaris supports, I think, almost all vendor specific file formats. Okay, what is good about Imaris? Why is it important that, why it is flexible to deal with the data, which is like a gigabytes of data, right? If the data is so huge, this is the good part of Imaris, that Imaris does not import all kind of information. Let's say, for example, this is a 20 gigabytes of file you have acquired. It doesn't import everything into the RAM. But what it does, it basically does a clever way. And the way it does is because of the Imaris file format. The way images are stored in a multi-resolution way, right? So it first stores the low resolution, and then the medium resolution, and then very high resolution. So the moment you see the first glance of the image, that's in the low resolution. And if you zoom in, then it asks the database to go for the high resolution thing. So it's basically, it's very smart way of interaction, unlike Fiji, for example. Yeah. So if your data is beyond your RAM, we cannot import. Yeah. Normally in all the other softwares, but this is like there is no limit. Yeah. Very important point here is that, and this software is free. So for example, you have acquired your data from the microscopes, let's say LIF format or LSM format. Then this software, which is called as a Imaris file converter, so it converts your file format, LIF file format, into Imaris file format. And this software is free. Okay, so I would advise you to install. This is a location I have given you because you are from Danstem now, so you can just go to this location and you can install free of cost. Both Mac and Windows versions are available, so that you can actually install on your laptop or whatever the machines, but not the Imaris workstation. So you will not lose time of your booking in just converting the data. You see, so you have already converted data, and that will be very fast. You just copy that data of Imaris converted and copy it to the network drive, and then start working from there. So copy the data from the network drive to your local drive, only Imaris file format, because you have already converted, right? And then start working on it at workstation. It's very simple use actually. Just it says add files here. Just click here and then go to your LIF or whatever the vendor specific format, and just hit on this one, start. So it will start converting all. That works for the batch processing. So it's not only one. You can select many images, let it run overnight, and then you have a result next day. All Imaris file formats. Okay. So let's start with then this is just a very brief introduction about the Imaris and the features of Imaris, and we should start with this visualization then. Okay. So Imaris, if you see the front end of the Imaris, that has been divided into 3 sub windows. So first, this is called as the object list, where you write your algorithm. These are the models basically. I don't know, have you were you present for the cell profiler workshop? No. Okay, but this is like a modular structure. So you just have to, click on the model that you are interested in, and you can make a list of models, and your data will be processed according to the list of the models. Okay, list of the operation that you have written. And for every module, if you click here, the properties box will come for that module. That's the second one. And the third one is a viewing area, meaning that whatever the data that you visualize, that will be shown to you here. And then the second window is called as a display adjustment, where you can actually control your channels and you can change the visualization. Yeah. So these are the 4 basic windows you'll be dealing with all the time. So let's start with Imaris. So this is how, as I said, first 2 and 3, right? So if you click on here, that's a volume, for example. So by default, the volume object list will always be there in the list. So these are the by default modules in the list: scene, light source, frame, and volume. The volume is basically what you see the data, right? So if you switch off this volume, the volume would be visualized, right? Okay, but then how do you basically import the data? It's very simple. It's just drag and drop. So right now we are not going to go to the arena, because we will see in the last. We will see now how to only process only single image, because that's the basic, right? If I start telling you all about arena, organizing the data set, I think it's become complex. So that we will leave it for the last session. We will just see how you import the data, just single file, and then write your algorithm on that. Okay. So for example, in this case here, my data is here. Program data, BITPLANE images. This one. This is my file, okay? And what if I do not have this? Let's say, or should I start from the beginning, very beginning? Or I guess, okay, you just have to double click the desktop and then this will come, okay? I don't have to show you explicitly how it goes. But just say drag and drop, you see here, okay? No, don't want to restart. Small. Just drag and drop like this, okay? So I'm not going to do that now, which is already there now. Okay, so this will appear now. Okay, the frame is basically this one. It shows you the grid, right? You can adjust the distance between the two grids, so do two vertical lines and horizontal lines. That will give you how big is your data set, right? Okay, and this window will appear. This is a display adjustment. Okay, so here you can control the channels, for example. So this example is the PTK2 cell, which has the kinetic core, that's represented by red, microtubule green, and DNA, that's in blue, and the denactin, that's in gray actually. So I think this is not important. Okay. How to operate on the volume? So it's very simple. It's like a left and right click. So right click is to pan, right, left, wherever you want. Zoom is for the scroll, this one, the mouse, and you can also do it with the left click, the turning, rotation. Okay, yeah. And let's say if you're confused that, okay, where was your initial location, then you can always click on the fit. So when you click on fit, it basically fit in such a way that you visualize the entire volume. Okay, and if you want to see it in the original location like XYZ, then you click on reset. So when you say reset, it goes to the XYZ normal. You don't have to do it like manually. You don't have to spend time on that. Okay, this is one thing. Okay, so if you click on this one, volume now, as I said, the properties will pop up here for that particular module. So by default, your visualization is in MIP. MIP stands for maximum intensity projection. Okay, that is the least expensive way of projecting 3D data on 2D. So what it does is basically, if you have a 3D data, it looks for every voxel and get a maximum intensity in that Z axis, okay, for that particular voxel, and just show you that 2D projection. Yeah. But let's say you can also go for blend view, normal shading, shadow projection. These are all computationally expensive, okay, and you have to use it very carefully, because the moment you click on this blend and if your graphics card is not powerful enough, this will crash. Okay, majority of the time, as far as DanceStem is concerned, you will have to work on MIP. Okay, there are some situation maybe for the cell tracking where there is an uneven illumination, where the background and the signal noise is not good, then I mean the contrast is not good, then you have to switch to the blend view. So what blend view does is that it also carries the depth information, because in MIP we lose that depth information because we go for MIP, right? But right now I'm not going to show you, but let's see, because I think my laptop is still powerful. You see the effect of blend, it has done very good background subtraction. So it has basically subtracted the background, and now I can see, okay, what are the structures are there. See, so depending on what is your use, right? Very important note here, you are not changing the data. This is just a visualization. You are not changing the data. Okay, this is for you, only for the user. Also with this this window, you can change the dynamic range of the particular channel. This is the same as PG. I think I don't have to explain this. This is the maximum range that I'm adapting now, and this is the minimum range. Okay, it's a minimum intensity. So all the intensity will be rescaled within this range. This center knob, that's called as a gamma correction. So be careful with this one. You are allowed to change this, okay, but according to the publication guidelines, it is always good if you do not change this. I mean, you are changing this for visualization, that's fine, but do not change the gamma, like for example this one, and okay, this looks very good now, okay, let's put it on the publication, the front page. No, you should not do that. Okay, and if you're doing that, you should mention that, okay, I have changed gamma from 1 to whatever it says. Yeah, gamma is basically a non-linear rescaling. Okay, so what it does is there is an input here in the x-axis and output on the y-axis, and depending on the curve, so normally there is a straight line, right? So whatever is the input, that's an output, but depending on convex and concave gamma, you can completely change the story of the picture. That's why it is not allowed. Let's say, for example, in this case, I want to highlight this microtubules, no, sorry, the kineticores, okay, and I want to reduce the microtubule, so I would do like this, you see, and then I would say, okay, actually in this sample there are less microtubules as compared to the others one, because I have just changed the gamma. See, so you can change the complete picture of statistics and the scientific theory, scientific evidence. So that's why it is not yeah, allowed to do this, even for the only for scientific publication. For data analysis, for sure, no. Okay, I mean, you cannot extract features from such kind of data. What is allowed is that as long as you're using this gamma correction and things like that just to make a mask, masking, you know, masking, we're going to see the masking, what is masking, and lay over that masking on the raw data and then extract features from that, that is allowed. Okay, we're going to see for the segmentation. So you can use gamma correction or whatever the fancy method for segmentation, as long as you're segmenting and you're mentioning how you're doing segmentation. Okay, but extraction has to come from the raw data, the real data. Okay, so this is all about, and you can always say reset all channels, so it will goes back to the original. Let's say if you have maybe messed up something, it goes back to original. Okay, and here you can see the gamma is changing. You see by default it's 1, and here the gamma is changing. You can change it to 2, and this is 2. Okay, good. So I say reset all the channels. Perfect. Right. Okay, this is all about this one. Then this is volume visualization. Okay, again I say fit reset. Right, what is this window? This window is the first section is a camera, right? So this is the entire section is a camera basically, and this is a pointer. So right now, in order to visualize volume, rotate, scale, zoom in, zoom out, by default it will be in the navigation mode. Okay, and when it is in select mode, you can't do anything. But then you would say, what is the importance of select mode? I think that will come when we do segmentation. Then we can select the segmented object. That time we have to have in select mode. Okay, camera type, by default it will be in the perspective. Okay, this is just the computer graphics modeling. So there are 2 views possible. There are so many other views, but the most majority of the time we use this perspective, right? And in perspective, it depends on how you look at the data. It changes that perception. So now it's a 45-degree. Look what happens now if I change data. You see, it basically gives the voxels which is very close to the user, it as if you feel like it's a 3D effect. Okay, even if the data is the same, it's just the visualization effect, you see. Okay, that's not important. This may be useful when you do an animation. Okay, orthogonal is very simple. Orthogonal is like XYZ. That's it. I will come to this point in the tracking or when you want to crop the data, then you have to use orthogonal view. Okay, but by default majority of the time you will be working with perspective, right? And in motion, this is just like it will, yeah, make your volume in the motion. This is also important, right? Because you must be wondering why they have given this. I think this is important when you segmented the data and you want to see, because if the data is like, if you have Z section and if you don't know which cells are like in the frontal view and then the back view, then in that case it helps. Okay, we will see this once we have a segmentation. Okay, and this is just to label the data basically once you segment it. So I think all the tabs are done here. Okay, Let's start. Let's say we have a data here now. We know how to interact with the channels. Okay. First thing you should check always once you have imported your data, whether or not your metadata is correct. Metadata, most important is the pixel size or voxel size. Okay. How to check that? Go to Edit tab and say Image Properties. This window will pop up, the properties. And you can see here the first one is geometry, saying that my volume is of size 256 by 256 by 32 Z slice. Okay. And there is no time points, it's just one time point. It's 8 MB of size, and the coordinates is in micrometer, and this is the voxel size. So 0.06 micrometer in X and Y, and 0.2 micrometer in Z. You all understood the meaning of voxel? Yeah, it's basically the size of the voxel. So this is the real distance which is captured by 1 pixel of your image, of your sample. So 0.06 micrometer in your reality is basically projected in 1 pixel. Okay, and this has to be okay. You don't have to worry about this one. I think normally it should be 0 0, but then everything start from basically a rectangular thing, and just say okay, right? Fit, reset. Exactly. But what if you, there's always a good idea, good practice to check it before, because what will happen, because when you import the data from the vendor specific data, there is always a chance of corruption of the metadata, right? And maybe somebody might have done the cropping and things like that and not taken care by of updating the voxel size, then you might get a false result. And let's say if you have done so many lengthy modular algorithm, then that algorithm you have to completely erase it, because it will not work on the, if you change the voxel size, because it has to compute right from scratch. Okay, so that's always a good practice to do that. Yes, exactly, that's a good question. So go to the vendor specific data. Let's say for example, do I have it here? I think I had somewhere. Let me see if I have it. Let's say for example, this is a lib file. Okay, open that in Fiji, and in Fiji there is a, I don't know, I think I don't want to spend time on this one, but I think it's very important for you guys to know, because many users ask me this. So see, this Fiji is open now. Okay, demand me later. I just drag and drop this lib file. It's reading the metadata now, and say okay, and this metadata is open, and this is somewhere they must have mentioned, and this is the data, that what is the size of pixel size of this of an image. You see here, that's a size basically, but they should mention the voxel size also somewhere. If it is not there, see, this is a problem. You see, because this is not visible here, so it's not there in the metadata. But let's say if you go to image now, and I say show info, in show info also it comes only this much information. Here you go. This one, got it? 0.107 and then 1 micrometer inside. So you should ensure this while importing an Imaris. Right? I close it now. Right. Okay. Let's start with the basic visualization then, right? Maybe you're not happy with this visualization. You can rotate, translate, zoom in, zoom out. You want to look more information, let's say Z by Z. Every slice you want to look at the information. How do you do that? You can just, by default, it will be in the 3D view. You can go to 3D slice mode, and then you can, this is Z, every Z. And if it is time point, then it will show you the time bar also here. And you can switch on and switch off all the channels that you want. Here, it just automatic, but I'll show you. That's a good question. You can change that also. Okay, the color and all stuff. We'll see that. Okay, this is also the slice mode. Let me finish with this slice mode. Okay, 2D, and then I'll remind me to go that. You can also go to section. You see, you can have the 3 planes at a time. So this is an XY, XZ, and YZ. Okay, there's a crosshair here, so you can actually click and see what's there in that section. Okay, you can also go to gallery. In the gallery, it will show you all the Z slices. Maybe it is just good to have a glance of your data right at once, or maybe for the presentations and stuff like that. Okay, and the third one is not important. It's basically they have been using this for a long time, so it's just the 3D, basically it's 3D view. Okay, coming back to changing the metadata, image properties. Yeah, we were here, right? To change here, you can change the voxel size and information. Then go to dataset here. In dataset, you can change the name of the data. Right now it says spindle formation in PTK2 cell, and this image is from Imaris itself. So you can actually give the courtesy, you can give the copyright information, or you can actually write your own information saying that, okay, this is the image which was approved by my supervisor, and I should be using for this one. So it is used. So all this information is there, right? Even if you come after 2-3 years, you know which image you have used for publication, right? Okay. Then go to this channel tab. So it will pop up all the channels, how many channels you have. So this for channel number 1, that's the name. This is how you can change the name of your channel. Here you can change the color of the channel. So right now it's red. You can give any different color just by clicking here. You can see here now. I can give the pink color, for example, to the kinetic core, and if I say OK, this will be reflected. You see here, pink color now. Okay. You can either go through this one, the edit and image properties, or you can directly click here to the channels. You see here, and this window will pop up. You can change the name. You can also write, okay, what this channel stands for. This information should come from the metadata, but that's not important for you. It's just if it is there, then it's fine. Otherwise, yeah, don't worry about that. Same thing for channel 2, other channels. Thumbnail, it is just asking how do you want to display this image. It's a thumbnail view, right? So I would go for MIP in this case. And the parameters, meaning that all kind of metadata. So this parameter will come from the metadata. But here you don't have to worry. It's just that information. That's it. But there is also possibility of making your own data set. For example, you can add groups here, and you can say, okay, this is the best collection or best replicate in my data set. But I think it's not going to happen. Okay, but there is a possibility of actually adding your own metadata in addition to the metadata from the vendor specific data. You see, there is a possibility of doing this. You can just say add groups and write your own metadata. Okay, so that's it. I will change the color for this one, not pink one, red. Okay, good. Okay, what if you want to, maybe let's say for example in this case, I do not want this denactin channel at all. I'm not going to use this even for segmentation, not for the quantification. Okay, and you will see the importance of this one when you have a terabytes of data or gigabytes of data. Because of only the one additional channel, it has to have all the information for all the channels, all the Z planes, all the time points. So why to have that? So there is a possibility of adding the channels and deleting the channels. How do you do that? Just go to edit and say delete channels. Here you just have to select which channel you do not want. I do not want denactin, so I would just say okay, don't want it. It's gone now completely. Okay. When you delete from this channel, it doesn't mean that you're deleting the raw data. Important, okay? Unless you save it and overwrite it, it's there. It's just you're changing the data now. Okay. As I said, you can also add channels. So if I say add channels here, and then I go back to my original file, and I say ptk2, you know what will happen? Because the size XYZ is same, it will just import the other layer of 3 channels in addition to already we have, right? So for example, I say ptk2 cell, you see how many channels are there now. It's basically duplication, right? But my point is that you can always go back to the original channel by just saying add channels from the raw data. We'll add it. Okay, now I think we have to delete it, right? So delete this. Right. Okay, any questions so far? No. Good. Okay, what if you have a very huge data? This is not a huge data, but maybe you have a, let's say you have taken the complete acquisition of the gut, for example, and you are only interested in one particular, or the entire pancreas, for example, and then you're only interested in one particular part of the pancreas, and you only want to quantify that part. But there is no point in taking all together the entire image. So maybe how to crop it, that's my point. So how to crop the data? For cropping the data, go to edit and just say crop 3D. So this window will pop up with the 3 planes, and here you can adjust your window. This is the region of interest that you are interested in, and you can adjust like that, for example. Okay. Here you can also either do it this way, interactive way, or you can just manually, if you know the coordinates, which is not going to happen, right? Normally you do it like this. If this had been a time-lapse data, there is also possibility of cropping the time points. You can explicitly say, okay, I'm only interested in from time 3 to time 34, for example. Yeah, so it will completely get rid of all the other time points. And just say okay once you do that. I'm not going to do that now, okay? This is how you crop the data. Okay. Change the data type. This you do not have to do it, and but there is also possibility of doing it, meaning that if you have acquired your data with a 16-bit high resolution, and let's say your computer is not working properly because the size is too big, there is a possibility of converting 16-bit to 8-bit. Of course, you lose a resolution, you lose an information, but it depends on your biological question. If you are only interested in how many cells are there, it doesn't matter if it's 16 or 8-bit. You're just interested in how many cells are there in the image. So in that case, I think it is a good idea to just convert from 16 to 8. So it was edit, and then last option, change data type. Okay. There is also possibility of resampling 3D. I think these are the options that I'm just telling you just because I have to conduct a workshop. I think you're hardly going to use this. Okay. But you can actually resample the data, meaning that okay, I want to basically not crop the data. I want to retain the same structure, but I want to resample it, meaning that resampling. So let's say your image has 256 by 256 pixels. You maybe decrease the size of the image by just taking every second or third. So first, third, fifth pixels in each direction. That's basically resampling. Of course, your resolution will be lost, but at least you will see the entire data set. Okay, so you might want to consider that. Yeah, and then this is an aspect ratio, which aspect ratio you want to preserve. Okay. I will use this only if your voxel size or voxel resolution is so good and you do not need it. Because if your voxel resolution is big and your data is big, then you need more pixels to accommodate that pixel. So maybe it's a good idea just to take every third pixel. Okay. Right. You can also delete slices. You can Z slices. You can delete that also. Just say here how many slices, which slice position you want to delete. So delete from all the time points also. So this is about interacting data and deleting. You can also add time points. I think I'll show you when we see the time point data. No, never. Be assured with that. Okay, important scale bar, right? So scale bar will be displayed based on the voxel size. Okay, but maybe you're not happy with the resolution of the scale bar. You want to change the length of the scale bar. You want to put it as a 10 micrometer, right? Then how do you do that? You have to change it to select mode here, and then you can change the length of the scale bar and the height of the scale bar. Okay, also maybe you're interested in this font size. That will also be changed through this one. Okay, you can change it through this one. Yeah, I think it's okay. I think you just pay attention here, because I think if you spend more time, then I have to wait for you guys before you finish writing. Is that, I think its recording will be done nicely. That's fine. Okay, so don't worry about so this is how you change the font size and this thing. Okay, good. Then what that's like cropping, deleting channels, visualization. Okay, so now we know how to add channels, add time points, delete Z slice, and things like that, interaction. And also we have seen the 2D 3D slice mode also. Okay, before we start even segmentation, let's look at it, what are the different ways we can visualize the data again, right, in a more fancy way. So one is called as an ortho slicer here. So all the models which you're going to work in the Imaris will be updated here. It will be enlisted here, right? So I'm basically clicking, just by clicking, right, the ortho slicer. So if I click on ortho slicer, this ortho slicer will appear here. And what this ortho slicer does, it does exactly the same as slice mode, but in 3D view. So you can actually rotate, right, which you cannot do it in slice mode. It will only show you XYZ, right? And also in addition to that, you can actually add as many ortho slicer as you want. So I added now ortho slicer for X and Y. Okay, once you add ortho slicer, it is a good idea to switch off the volume, otherwise you don't see this importance of ortho slicer. If you switch off the ortho slicer now, you see it is showing you now the XY plane. How to run over different Z slice? You have to be on the select mode, because if you're in navigation mode, you won't be able to interact with the slice. Okay, so you have to have the select mode, and then you can see the information. You can zoom in also simultaneously and see, okay, what's there, right? Okay, as I said, you can add multiple ortho slicer, and maybe this time I want the other ortho slicer. How do you change the plane? Here, just by clicking, right? Now it's YZ plane now. So we have two ortho slicer now, one here and one here, and I can go and see, okay, what's there actually in this cross. I can see that, right, information nicely. Yeah, so it depends on what do you want to visualize. Okay, this extended section, this is the width of that slice. Okay, so that is by default just one pixel, one voxel size, but you can change that width, right? Maybe you're not interested in looking at every voxel size information, but maybe just kind of approximate, right? So you can change that also, right? Okay, so I delete this now. Okay, how to delete? Just select it and just click on this one. So this will be gone. Switch on the volume, you're back to normal. Okay, maybe I'm not satisfied with the ortho slicer. I want something again more fancy so that I can visualize in arbitrary orientation. So for that you can go for the oblique slicer. In the oblique slicer, it gives you this handle. Okay, so there are two rods here, well, two cylinder I would say. So it's a bigger cylinder and the smaller cylinder. Change it to select mode. The bigger cylinder will give you exactly, you can iterate over the different Z section, right? And the smaller cylinder, you can change the orientation, right? Again, you switch off the volume so that you see the importance of this. Now, if you want to iterate in this direction, which is completely arbitrary now, you can just say like this. This has importance when you have a very nice anatomical information. Okay, this is not a good example, but the reason why I'm taking this example is because it's a light information, a light example, because then I don't want to crash my laptop. But maybe let's say, for example, you are working at pancreas. I have worked with many examples from your dance stem where it's very useful just to see what if there is an information which is embedded not in the XY and XZ and YZ plane but some other planes. Then it is a good tool actually to look at the data. Okay, you can also zoom in this one and see what's there. Okay, yeah. Mm-hmm. Exactly. Yes, yes, that's true. You're completely right. Okay, but oblique slicer and ortho slicer works on volume. Okay, it will not work on segmented data. If you want the segmented data to also work, then that's the next model that we're going to see. Okay, so everything clear with this oblique model? Just delete this now. Okay, coming back to your question now. Maybe you're interested in yeah, doing the oblique slicer but also on the segmented data. Okay, then there is something called as a clipping plane. You see Caesar here? So say clipping plane. If you click on clicking plane, then you can say it's the same thing. The bigger cylinder, smaller cylinder, it's reducing. See the importance of the clipping plane? It's not an ortho slicer or oblique slicer. It just displays whatever is there down this one. See, beneath this one or under this one, I would say. Yeah, and you can also change the direction of this. Maybe I want to see what's there, so I'm changing it. You see here, right? Good. Sequence. You can also add clipping plane at the same time, but I doesn't make sense to have, because I think they have their own importance, right, at one time point, because I don't see the importance of having ortho slicer having the clipping plane. You understand my point? Yeah. Yeah. Right. But cropping, you can do it there. This is not a cropping. This is just aiding a visualization. Okay. For a cropping, you have to do it what we have seen, 3D crop here. Yeah. Yeah. I mean, you're right. I mean, the cropping is not possible in arbitrary plane. No, that's not possible, because in order to store the data, still we are in digital world, right? So we have to have XYZ. I mean, the coordinates, right? Um, yeah. It would have been very nice if we store just what we want. Yeah, unfortunately we can't. I mean, we can do a zero padding, right? Just crop that part and then we can add zero padding, but it has to have a rectangular size as an image format. Okay, but this is clear. Good. Right. And you can change the sequence of this one. So depending on the sequence, you can also have a different clipping planes, right? You can switch on and switch on. I will show you that during the animation. You can switch on and switch off different clipping planes, because maybe for certain time point you want to show only this clipping plane and then switch off this clipping plane, switch on the other one. So you can have multiple clipping plane. Okay. You see, now I would say fit, so I don't have to worry about, and then reset. That's it. Change it to smooth. Okay. We haven't even started actually segmentation, but actually this is good, right? So you understand how to interact with the data, visualization, and things like that. Okay. I think I'll put my mobile because this watch is not correct. 152. So this is until 4 o'clock, okay? Good. Right. What next? Yes, that's a good idea just to there is a one tab from this Imaris recent version. I mean, it has been there for a long time, but there is a Fiji tab here. Okay, Fiji. So what if you want to do some kind of a pre-processing? Okay, I'm just talking now. Okay, let's say before you even start your segmentation, you want to pre-process the data, meaning that you want to smooth your channels, Gaussian smoothing or median filtering, things like that. That you can do it from here, the image processing tab. Image processing, go to smoothing, then Gaussian filter, and the Gaussian filter is nothing but the smoothing, okay? And here you can select the channels on which you want to apply the smoothing. Let's say, which channel do you want me to smooth? Let's say microtubule, okay? So switch off, select microtubules, and this filter size, this is proportional to the voxel size. So by default it is, I think, 2 times of the voxel, okay? But if you want more smoothing, increase this value. Now see what happens if I go to, let's say, 0.7, for example. No, 6 is already there, but let's say 0.1. See what happens to microtubule now. Okay, I say apply. See, it has smoothened this channel. Okay, you would be asking, wondering why I have to do this. The reason why I have to do this may be the segmentation. With a raw channel, the segmentation is not accurate. Maybe there are a lot of false positives because there are a lot of uneven illumination. And to get rid of this uneven illumination, you might want to change this channel, which I'm doing now, smoothing. But then again, coming back to the original question, once you have changed this data, can you extract the information from that? You should not. To extract, once you have made a mask out of this microtubule, let's say, you go back to, here you say OK, you go back to edit and you say add channels and go back to the original one, original image, yeah, and say PTK to cell. Because once you have that mask, then you delete this channel which you have created and use the raw channel to get the information. Understand? Okay, let's do one thing. Forget about this smoothing now. Let's ask ourselves a question that this is an image, and our hypothesis is now that we want to segment this nuclei, DAPI basically, DNA, and we also want to segment this vesicles, the microtubules, and the kineticores, the spots, and the microtubules, and then see how far are these kineticores are from the microtubules. Okay, first start with the very basic. Let's segment DNA, which is in channel blue, right? So for that, I have two options. That's a spot and the surface. This is very important, okay? In Imaris, you have only two choice of segmentation. Spot or surface. When to use what? Spot, one should use it when you have a spot-like structure that you are interested in. Like for example, in this case, I would go for kinetic core because they look like a spot-like structure, right? While in case of DNA, it is not a separated structure. It's not a well-defined structure. And its geometry, its morphology, and the shape is completely arbitrary. In this case, I would go for surface because it's a surface. So for that, you just click on the surface tab here, surface. The surface model is created here. Maybe you would like to change the name of the surface. Maybe it's very confusing to you what is the surface to. So just double click this and say, okay, I want to segment and label this as a DNA. Okay. We haven't even started now because this is, once I click here, this window will pop up. This is the properties of that particular module. And because this is surface or the spot module, it has a wizard. It has a different steps in order to create the surface. We haven't created yet, but we are at the first step of the 4th step. Okay. Here it is asking me, okay, algorithm, skip automatic creation and edit manually. It is asking me, do you want Imaris to do it, segmentation for you, or you want to do it by yourself? I would say, okay, automatic. Favorite creation parameter, I'll come back to this later. Don't have to worry about this one. Algorithm setting, segment only region of interest. As I said before, you have two options. Either you can create before you start segmenting. Okay, you crop the data, or you can do it here, segment only region of interest. So you have your entire data, but you're asking algorithm to only process this region of interest. That is also possible. The moment you do that, you get the same stuff. If you go to the next step, you see this window, you had the same thing when you go for the 3D crop. Okay, but here you can change the window size now. Let's do that because then you will also understand the importance of this one. So in this case, I would change it to orthogonal view so that I can visualize the knob. Basically here I have to change it to select mode. You see what I'm doing now? I don't have to do it right now, but I'm just telling you this importance of doing this. Change this one. Okay, and then say next. And next, it's asking on which channel you want to apply, because see there are 4 channels, actually 3 channels, because when you delete it, it is asking on which channel you want to apply this DNA surface. So it's blue channel. Smoothing is important. Again, coming back to this, why we are doing smoothing, right? So you have two options. You can change the smoothing channel a priori to this wizard creation, or you can do it in between. I think this is the best option because you don't have to go back to the raw data and then get the original information. So here, just for segmentation, I'm doing smoothing. So here I would put 0.1, right? Okay, this is real information of segmentation. You remember what? Okay, everybody knows what is segmentation. Segmentation is nothing but you have an image, you're telling computer automatically, or computer will decide automatically the region of interest that you would wish to see it. That's a segmentation. Okay, and segmentation happens based on thresholding. So if you have a, okay, I'll show you. So in the thresholding, you have a 2 options. One is absolute thresholding, absolute intensity, and the background correction. I'm not going to do the background correction. I'll come back to it later. Let's go for the very simple absolute. What happens if I go to next? This one I was talking about. Okay, so this is the histogram of this entire blue channel. This is 255 maximum intensity and minimum intensity, and this is my threshold. What I'm telling computer is that all the voxels whose intensity is above 75, consider them as a DAPI, consider them as a DNA. and that actually changes according to which threshold you use it. You got it? If I am here, all the voxel whose intensity is above 209 is only displayed, which is very, this must be a very high intense voxels within. You understanding this point? Okay. Then the question is, how do I select this threshold? Right. So this has to be set by the user, because you need an information, biological information. But majority of the time, what happens is this automatic works very well. This when you click on this automatic thresholding, it calculates this threshold automatically using Otsu algorithm. Okay, this is a algorithm which calculates threshold automatically, right? And this is okay until this point. Yeah, okay. I'll come back to this later about sometime what happens that this segmentation, you're not satisfied with the segmentation because the two entities are touching together and you want to cut them, but that you have to do it like not manually but automatically. In that case, you have to switch on this enable split touching object. I have an option for that. I mean, I have an example. We'll come back to that one. But let's go forward, because now I'm only interested in this. What is the surface of this DNA? Right. What is the volume of the DNA in this sample? Go next. So it has created now the surface. The second, the last step of the wizard is classify surfaces. Maybe there are some outliers in the segmentation profile, which you do not want to consider that as a DNA. Then there is a possibility of selecting different criteria on the basis of which you will filter the surfaces. So by default is number of voxel, meaning that the volume, right? Maybe what if I'm only interested in the bigger volume, the biggest volume. This is the biggest now, you see. This was there, which was separated. So likewise, I can actually filter with size. If I want the smallest one, then I can just click here. This would only select it. Yeah. And accordingly, I can have a different criteria here. This is just one of the criteria. And I can keep on going and adding different criteria to select the option, the filter, the population that you are interested in. Yes. Yeah. I'll come back to that later. Okay. So then that's it. That's the final stage, right? Just click on this and done. Your surface is created now. Okay, it's calculating. It's my laptop, right? So, oops, and it crashed. Okay. So this will happen majority of the time. But right now, because we're also recording, right, and this is also a laptop which has a not very good graphics card, so this will happen. But I think if you're working on the workstation, it should not happen, right? So going back to original one then. Normally it is fast, but because we have imported data from the network, then sometimes it takes time the database entry to update, right? So be patient. Workstations. Okay, coming back to now workstations images. I'll do it very fast now. Okay. Oh no, I don't know what is happening now. Um, it just doesn't allow me to do it. It allows you to export the data. You can save in between also, but if sometime it crashes without any reason, then of course everything is gone, right? Oh yeah, yeah, of course. Yeah, yeah, exactly. Yes, yeah, yeah. Yes, this is so actually because normally it should not work. We are just working on very simple data. I don't know why it is behaving like this. Mm, maybe just say delete channels. Let's say I don't want to work on this one. Let's go for very simple ESL. Say yes. Okay, this is good. Good. At least for this one didn't crash. Okay, I think it's because also we are recording simultaneously, so maybe it's a lot of overhead for the operating system. Okay, um, but I think I don't have to explain you what is this example, right? Here I've just segmented the nucleus using the surface, um, and also I can do the same thing for the cytoplasm. Oh, by the way, this is a time-lapse data. Okay, so you see, yes, yeah. So if you switch off, let's look at the original data now. So this is the original data. Okay, so if you import this data, this is the image. That's the division of the cell. Okay, right. Okay, so we're working on this data set now. It's just a cell which is dividing and then splitting into two nuclei. Okay, and we have done segmentation on the nuclei, which is the red channel. Yeah. So it's here. It's for you just to So it's done very well. Okay. There is also possibility of doing this, as I said, the segmentation based on not the absolute intensity, but I think this is not a good example because this is really nice. It's really nicely segmented, right? But there are some examples. Hopefully that time it doesn't crash. But I wanted to show you how do you improve the quality of segmentation based on background correction, not the absolute intensity. I will come to that point. Let's see. Okay, for the cytoplasm, um, I really do not want this one. Okay, but now you understand the surface creation. Okay, let's go back to the data again and mm, go for maybe this one. Hopefully it doesn't crash this time. Right. This is also an example, it's very simple example of the cell wall and the chloroplast cells, right? The cell wall. Okay, now here my interest is to know how many chloroplast cells are there in this case. So if I ask you a question that if my only interest is to know how many chloroplast cells I want to quantify, should I go for surface or should I go for spots? Spots, right? Because I don't care uh, how different they are in the shape or the morphology. I don't care about that. In that case, I would go for spots, right? But if I'm interested in knowing, okay, what is the volume? What is the, because there are different in volume, they're different in size and shapes. So in that case, the spot will not carry that information. Spot will have the exactly same radius for everybody, right? So this is how you have to decide between the surface and spots. So let's go for now the spots, okay, for this one. So click on the spots and I would say cells. Okay, next. Yeah, for the spot, it's the same thing as what we had, like segment region of interest. Maybe you're interested only in the region of interest here. Different spot size. It also allows you to have the different spot size. But let's go first that I'm not interested in different spot size, because you know, as I said before, when you select a spot, the size of the object is proportional to the diameter of the spots. Okay, and everybody will have the same diameter, right? But there is an option of saying this diameter is proportional to the size of the object. So at least you don't get a morphology, shape information, but at least you get the size information using the spots, roughly. So there is a possibility of doing that then. Okay, but I would not do that now. Okay, then select this channel. Spot detection. Okay, for spot detection, it is important to know what is the approximate diameter of your object of interest that you want to call that as a spots, right? So of course here it is not possible, right? I cannot do a measurement here on 3D. So to do the measurement, you have to go to slice mode. In slice mode, I have to select a slice where I can see the cell that I'm interested in. I think this is good, this slice. Okay, how do I measure then? Just by default you are in the line mode. Click here and click here. It will display how much is that length. That length is around 5.8 micrometer. So I know the approximate size of the cell should be around 5, 3 or 4. I would go for 4, just an average. But this is very empirical. You have to come back and see the result and do it again. Okay. I would say, so it says 2.5. I would say, okay, I'll go for 3 or 3.5. Here it was a point of background subtraction. Why background subtraction is important? You remember that we have done just an absolute segmentation, absolute thresholding, meaning that you have a histogram of this entire image and then you just select a threshold. This will work only if you have a very nice background, smooth background, meaning that the black background. Okay, but sometimes it doesn't happen in the microscopy, especially confocal microscopy. You have uneven illumination. In this case, you see not all cells have the same intensity. Their intensity is variation. So in this case, the background subtraction is important. So what it does in the background is that it does this rolling ball algorithm. It's also called as the Mexican hat algorithm. It considers this as a size of your Mexican hat, and it goes on putting that Mexican hat on everybody. Okay, this is just a metaphor basically. Algorithm works in different ways. Also, it has the analogy of rolling ball, as if you are just throwing a ball of a certain radius, which is basically of this diameter. Yeah, and you're throwing that ball over the entire image, and consider that the intensity is nothing but a peak, right? And depending on the size of the ball and the intensity and the distance between the two peaks, the size, the ball might go in between the two peaks or it just topple over. This is how it comes to know what is the profile basically and try to reduce. Okay, I don't have to explain. Just use this one. Okay, and just click the next. See, the spot has been created. It's very beautiful, right? And very intelligent. But there is a problem here. You see what is the problem? The problem is that for one cell, it is taking the two spots. So what is the reason behind this? Why is it doing this? Any guesses? You see here also it's doing that. Yes, exactly. So there are two peaks basically within the one cell. There are two maximas, and because we have said okay, I have to do background correction. It's just taking the background rolling ball of that size, right? Maybe what we should do is that I think we should increase the size of our ball, rolling ball. So we go back and change it to, let's say, 4 or something. Let's see what happens. Very good. We don't have multiple, well, we just have, actually it has been reduced, right? There are some, like for example this one here, but at least the size of the ball has been reduced now. There is one example here. There's two balls here. Lower one, yes. So first, there are so many parameters here, okay? Be aware of this now. Once you are here, there is this quality parameter. What is quality again, you say? Quality is, I would say, there is an algorithm behind this one to generate this spot, okay? And the spot is generated based on the quality factor. There is an algorithm, as I say, Mexican hat algorithm. So what that Mexican hat does is that for every guys, every contender here, it gives how best it fits to the original model of the Mexican hat. And depending on that, everybody will get a quality factor, quality criteria. So, and this is a quality scale. So if you are in the right side, you have more probability of being more closer to the model that you have built. So if I'm going here, let's say here, these are the best contender for the model. You understanding my point now here? And the moment you go to the left side, these are the best contender actually for the model to be fitted on this one. Okay. And if you go this side, oh, there are so many outliers now. You see, this is also basically a model is fitting. You do not want these guys to be as called as a cell. That's why you have to select this criteria of quality in such a way that you are satisfied as a user. Okay. Right. I would go back and change it to, let's say, 5 or something. Let's say. This look a bit realistic now. Okay. And again, you can change it. We can keep on spending time on this one, but now you understand the idea, right? This is something that you as a user has to do this back and forth. Okay. I rely on this automatic quality thresholding. I go and hit this button. That's it. I'm done with the spots. Right? Here the problem here is that you won't be able to visualize the spot because it has given by default the same color as the channel. Maybe in this case you want to change the color of the spots. So once you have created the spots, the additional tabs will be open for you here. By default you will be in the first mode, which is kind of visualization point style. So it is in sphere mode. You can actually go to the center mode. Then you can only see, okay, the center points. Change the color, the second last tab, color tab. Don't go for label, go for the base, and in the base you can change the color. You see, changing the color now. Go back to the first one, center point. You can change the width of the center point. I mean the radius, like this. Or again for sphere, they are very big, right? Because we have selected the same size of the spots. That's why. But I think, yeah, you can then reduce this a little bit, 0.5 for example. Then you can see. Okay, good. Right. As I said, our whole idea was to know how many cells are there in this whole sample. So this tab, statistics tab, will give you all the information. Actually, this is the real information what we want, why we do all this practice. So if you click on this one, it will give you all the information of that objects. So it says number of spots per time point is 180. So there are 180 spots here. But maybe you're not interested in these spots, which are at the actually boundary. They're incomplete. So there are several ways of getting rid of this spots. You can do it manually, as you asked, right? How to delete manually some points. So let's see that first, okay? Let's see that I'm not interested in these guys over here at the boundary. and there are some few which are basically outlier. So how to do that? Go to the third tab here, and then you go to select mode, select, click this one. You can say, you can keep on control, because if you want multiple spots to be detected or deleted, zoom in here, control, control, select, select, and then say delete. They are gone now. Got it? And likewise you can do it from there. But at some point, you know, if your data is so huge, you don't know, there's no it's not realistic to do it manually, right? So there is also possibility of doing this based on some criteria. Okay, and that criteria will be on the fourth tab, that's called the filtering, this funnel symbol. Here you can add all the criteria. The criteria could be shape. Here shape doesn't matter because everybody is like a spheroid. But here actually you can add some intensity information, some geographical location, like how are they distributed in the entire image. So here you can see distance to the image border, XY or XYZ. If you select that, then you are only selecting these guys which are at the center. Got it? And this is the distance, meaning that just imagine that you're actually quantifying from here the distance left to right. Right? You do not want these guys. You just click, right click. So they're also gone now. Or I would go for the XY distance. In this XY distance, I would go for this one. Okay. Okay, it's basically, it depends on what is its XYZ, right? Because then that you have to see it from this. If you go here, fit, reset, this is its XY. It was wrong what we are saying, right? It's just, this is X and this is Y, right? So left to right, that's what it's increasing. But you can have a multiple such options. So for example, XYZ border, and I would say, okay, maybe somewhere we'll reach to a conclusion where we will get rid of these guys. Yeah, we still have this one too. Yeah, exactly. So I would go back and I would say, okay, duplicate selection to the new spot. Okay, I would select this. This is created. I come back here, and because I know I do not want these two guys, which is very extra, and that I can do it actually manually. Just go there, here, select, control, control, and they're gone now. Okay, but this is not always the case. You will always find some criteria which would suit your application. It's just that we have to spend time in considering, right? Okay. We can also generate a channel which would say a neighboring distance. So it basically calculates the distance of every spot with its neighbor. Okay. And then what will happen to these guys? Because these guys are away from other guys, they will get some different values. And based on that value, we will separate them. So there are multiple ways you get rid of that. Okay. So, but this is how you create the filtered object now, and you can then go to the statistics tab and see, okay, how many cells are there actually in the one region biologically relevant. That's 163. You can go to detail tabs and go for area. You see, area is the same for everybody because this is spheroid. But you can just go to the intensity of all the channels. Maybe I'm interested in knowing the mean intensity of a chloroplast cell. This is the mean intensity of all the cells. You can also go to the average values. In the average values, it calculates average of everybody within that image. So if you go to the intensity, mean intensity of you see here, mean intensity of channel number 1, 2. This is the mean intensity of the entire section of this intensity that you can compare with other condition. Okay, you can also, there is also possibility of extracting the information of the one interesting time point object of interest. Let's say I'm interested in knowing, okay, this guy looks very interesting, but that for that you have to be on the selection tab, and then it gets an information for that particular object here, all this information, all the parameters for that particular object. Okay, all right. You have selected this one, and maybe you actually you're zoomed out a little bit, you don't know what you have selected. Go fit to selection, select something and say fit to selection. See what happens. It automatically zoomed into that one. Isn't it beautiful? And then slightly just zoom out, but at least you know where you're looking at, right? Okay. Center to selection, that's also actually interesting, because if we click there and center and say center to selection, that's basically in the center, that particular point. The entire volume moves and then put it in that center, and then say fit to selection, then you know, okay, where you are, right, like this. And maybe here it is important to have this in motion. You see, now I know, okay, this blue one is basically behind this blue guy, just because I'm in motion now. I can see, okay. Yeah, it's always like that, but do not use it, okay, if you have a huge data, otherwise the things will crash. I'm just to show you, I never used it, okay, but I'm just telling you there is an option of doing this. Don't do it. I think I would do like this instead. Okay. So far so good. I said how to change the color also. There is also possibility of doing the coloring not like a single color, but a color based on some criteria. So that is the statistics code. So if I click on this and I say area is, there is a warning for area because everybody has the same area. But what if I want to display the color based on the mean intensity of chloroplast? Okay, then I would go for, or I would go for this one, distance to image border XYZ. And this is my color bar. So this gives you an idea. Okay, I think this guy is basically it's far away from the XYZ. The reason why I have told you is basically you can understand the meaning by which the Imaris works for every object. This is not so this normally I do not use it, right? I will use this just to get an idea where should be my threshold in order to get rid of the, you remember that outlier that I was talking about? Just to get an idea what should be my threshold, because then I know, okay, if this is my outlier, I know what is the color of that, and accordingly I will set that threshold, right? But normally our idea was to basically use mean intensity of channel number 2. You see now, and you can agree with this one, right? Because these are all the bright cell chloroplast cells, and they have got something kind of a yellow color, while these one they have the faint color. Yeah, and then accordingly you can use many different criterias. See the position of X, position of Y. You can see that it's X starts from here, Y is here, likewise. Yeah, you know that. Okay, you can also change the transparencies just so that you can also visualize the data also, and also I think this is important when you have a surface. Okay, but everything is clear with the cells now, the spots creation. Okay, I'm gonna delete this. Okay, let's create now the surface, but I will tell you why surface and then this watershed algorithm. Right, let's create surface. Here my idea is now I am also interested in knowing the
volume of the individual chloroplast. Not only that, how many are they, but how big are they, shape and size. In this case, I will use surface for this. So surface, I would say cell. Next, use this one. See, for smoothing, this option is there. Like for surface, the smoothing option is there. For spot creation, smoothing is not necessary. Okay, because surface needs to be smooth, right? That's why smoothing is important. And also it is important for other mathematical reason, right? Because when you create surface, you basically create a triangulation, all the meshes structure, mesh and vertices. So for that, it is very important to have a nice smoothing structure. Otherwise, again, it will crash. So let's say 0.5. Okay, I'm sticking to the 0.5 then. Here we have seen already this algorithm of absolute. This time we'll just take for the background correction, background subtraction. Now again, the same thing as a background subtraction. You remember for spot creation, it asks us about the rough estimate of the diameter. Same thing we have to give here. What is the diameter of the largest sphere that fits into the object? Okay, because we have already know roughly what is the size, so I would put here, let's say 3 or something, and go next. That's a surface. Okay, but again, this surface is based on this threshold. The moment you change this, surface would change accordingly. Right? If you are more, then there is a problem of intertouching cells. But don't worry about that. We have a solution. But at least you should be, you should have to make a compromise between these two, right? You should not be too much here in the left, too much in the right, because that's called as a under segmentation. This is over segmentation. You should be here somewhere, or look for automatic. What automatic says. I think this is good. Majority of the time it works good. But here there is a problem. You see, these guys are touching together. How to resolve this? For that, you say enable split touching objects, right? But it doesn't come automatic. It needs to know some kind of rough estimate of what is the average size of your object. For sure, the size of this object is bigger than what we have given, like 3. So it is asking us what is the seed point diameter, meaning that I have this one object. If I want to divide this object, what should be the minimum size of maximum size of the seed diameter? Meaning that the diameter of the, how would you expect? I mean, if this is my object, and if this object is 6 micron, and if I say 3, computer knows, okay, I have to divide into 2. Likewise. So I would go for, I think I'll stick to 2.5. Let's see what happens. Go next. Now it is trying to create a seed points. Okay, I know it is a bit confusing now. We have created surface, right? In the previous step, surface is still there. Because we have asked computer that, okay, I'm not happy with this surface because surface is like this. I want to cut it like this. Now in the next steps, the computer is asking, okay, I can cut for you, but I don't know where to cut. I need to know some seed points, the location of the seed point, so that I know if the seed points are here and the things are here, I can cut it like this. Agree? Okay, this is what we're doing now. Surface is still there in the previous step. No, the surface is still there, but the seed point is created by spots. The seed points, in order to cut the surface, is created by spots. Now this will go till we create the seed points. After that, it will forget about the seed points once it has cut and go back to the surface. Got it? Okay. But here there is a problem. You see, the seed points, they are more than it is required. So what will happen to this one? It will cut here surface, that's fine. Here it will cut it here, but it will also cut it like this. We do not want that, right? So what should we do? As we had before, exactly. So go back, and maybe we have to increase the seed point, right? 3.5. Let's see what happens. Got it. But again, this is just the one case. You will find some false positives, but you have to then make a compromise, right? Yeah, as long as the false positives are in a minority, that's fine. Your statistics is not going to affect by the outlier if you're doing a median yeah, calculation. So yeah, for the sake of time, I'm just sticking to this one, but you can always optimize. I go next and see what happens now. It has forgotten all the seed points and now went back to the surface, and it has cut according to the where there was a seed points. You see, it has cut accordingly. Yeah, this is what we want. But maybe we are not happy. Well, okay, let's say fine, we are happy with this one. As usual, I can classify, I can filter surfaces based on some criteria. Let's go for the, maybe I do not want these guys over here. You see, they are very awkward in shape. See, they're not very good in shape. So maybe I can use sphericity as a criteria. Sphericity, that's a shape criteria, right? Because we have chosen now surface, we have a possibility of extracting this information, shape information. So here, not only I use the voxel size information, that I want all the bigger voxels. Actually, I would do the other way around. I would do it like this. I do not want the smallest one, but I also do not want the largest one. So I'm happy with this one now. Okay. And on top of this, I want to add another criteria. I would say add, but now I want the sphericity as a criteria. Do I have a sphericity? Yeah, sphericity. Got it? So this is my sphericity. In addition to the size of the surfaces, cells, I'm also adding, I want those cells whose sphericity is at least 0.65. See, more is a sphericity, more is a spheroid in the shape, right? So if you see here now, these are the, you can see it. They are very spherical in shape. So if you want a very nice cell, you can just go for this one. Right? If you want, okay, like this, maybe this point here. Fine. And hit on the next. Finish. You have done with your, and then crash. Okay, because we're doing so many. Yeah. For that, there is no possibility. First of all, in Imaris you can't say that. But in order to, if you want a smooth partition between these two guys, then you have to smooth your data before you fed it to the Imaris. Because everything is based on, this is a watershed algorithm, okay? The way it works is that, imagine that this image, just a minute. Again, consider that these images is, you're looking this image, XYZ, but the Z axis is intensity. So wherever there are peaks, it looks like it's a peak and the valley, peak and valley for all the intensities. Watershed is that, imagine you are pouring water from the top. Of course, water will not stay on the peak, right? It will go to the catchment basin. And depending on where the catchment basins are, computer needs to know, okay, now I have to cut it here. If there are two peaks like that, sorry, like this, right? The water will stay here, water will stay there, like this. And then computer needs to know, okay, this is how I have to cut it. To have the nice smooth catchment, you smooth the data. Then you have a very nice kind of a boundary between these two. Got it? Good. Okay, but I think it's really good that it crashed once we have done. Okay. Let's do that again. Surfaces, chloroplast. I would go for absolute, okay, just to show you. Oh no. Maybe we need a simple data set to work with. It keep on crashing. It's good because I'm recording and putting on YouTube. So maybe if the Imaris guys, if you're looking at this one, this is 9.0.2. It's the latest version and it's just crashing on the sample data set. So it's good for them. At least it should work for the sample data set that they have provided, right? So, okay. But that's also good from the Imaris because it's really nice of their development team that because every time they develop, right, they update their softwares. So they are very upfront for development. So okay, which data set we should take now? Let's take this one. Right. Okay. So we are done with surfaces, spots. I wanted to actually show you the arena, the vantage view. For that, I will use this this data set. This data set is a time point. See, the cells are dividing, right? And I want to know with this nuclei. This is a nuclei thing. First, I will segment it, and I want to know over the time how the intensity changes. See, before mitosis, after mitosis, and things like that. So let's create surface now. Track, okay, forget about track because when I take track, I will come to know. I'll get back to this tracking stuff, okay, when we go for the tracking. Then the red channel with absolute intensity. Don't crash it now. And go this one. No, I don't know why it's doing this. Okay. One more try. Okay. This is how segmented. See, there is a problem. This has not been segmented. See, there was some time point where this two spindles, one of them were did not segmented. See, and maybe this time I should go back and oh, there is actually there was. It's just that's not visible. I think there was. Let's go next. Maybe this size criteria. See, size. So just say delete this. I do not want this size to filter out. Because here we know it's just one cell, so we do not want to get rid of the outlier. But now it's this one here. And hit this button. Oh, I'm a bit skeptical now. Okay. Oh, I don't know why it's doing this. Right. Okay. Should we take like a 5 minutes break and I will restart my machine? Maybe that would help. Okay. So please come back after 5 minutes. Yes. Okay. So should we start now? So we just have 1 hour left, I guess, right? No, 2 hours left. No, it's 3 o'clock. Okay, so in 1 hour left. Okay, so we should do now tracking. This is very important. Okay, cell tracking, and we will see the co-localization, a little bit of co-localization, or maybe it's your choice. Maybe if you can If you want me to go for how do you make a manual annotations and manual surface creation, because in most of the time the dance stem you're not happy with the segmentation what Imaris provides, right? You basically want to draw and segment according to the region of interest. Maybe we can do for that. Okay, we will see how much we spend time on the tracking. Okay, so for tracking, there is one example. Considering our history of crashing the computer, I had one example of the dance stem, the cell division and cell cycle stuff, right? I wanted to show you, but just to clear your concept, we will use standard BITPLANE image, which is the algae cell movement, okay, which is this one basically. So this is the image basically. It's just a brownie. Basically, they're just moving, right? The cells are moving. This is the time-lapse data, as you can see here, and that's they're moving. The swimming algae, right? Just swimming. This is only one plane. We can also take the 3D, but then we have more chances of crashing. So just for the there are two, yeah. But you're right, it's 2D. But I think for the clearing the concept of tracking, I think should be enough, right? Right. So our challenge is now we want to track individual this algae cells, or whatever algae you can say, or algae you say, and see if they are, and and see what is their movement, right, across the time, how much intensity variations they have across the time. I know it is not very interesting because you guys are developmental biologists, right? But if you apply this algorithm here, you can apply the same thing for that data set. Okay, so for this again you have to ask two questions. I mean one question to decide the two options. Do you want to go for the surface or the spot here? Because you can track spot, you can track surfaces, but which one? Spot, right? Because that's less expensive computationally, and also you're interested only the track, right? But maybe if you're interested in some application that you want to see how the morphology of the cell or the nuclei changes from, let's say, G1 phase to S phase and then G2 phase, and like such application, you can go for the surface. But do it on workstation, not on laptop. Okay, so I stop this now. Go here, create spots here, give name L key, algae cell, and again I have an option. Let's do this time an option of different spot size. Maybe you will also get a feeling of, you know, what if we take different spot size. But again, I think our chances of crashing will be more. Let's see, okay, for the sake of science and understanding, we can still come back. Different spot size, go next. There is only one channel, there is no option here. Estimated XY diameter. Let's go back to slice mode and see what is the diameter of this one. So that's around 5.17 micrometer. Okay, go back here. What does it say? It's around 10 micrometer. Okay, you wanna go for that? Should we reduce this? Let's go for 7. Background subtraction. You see, this is important. Why do you need background subtraction? But you see here, this is a black part and this is very bright spot. This is uneven illumination. So if you use now without background correction, background subtraction, we have lots of false positives. So let's go next. Very good. As we had before, this thresholding, I think we are good for this one, but you should not check only one time point. You should check all the time points. See if it has done very good job in, I think, optimal job. It won't be, it's not possible. This data set is very simple. Majority of the time you have to also always go back and forth and change the parameters. Okay, but now you can see it. I think it's very good. Go next. Because we have selected the different spot size, there are two algorithms for this. Do you want to go for the absolute intensity or local contrast? Okay. Again, with the absolute intensity, it tries to expand, because right now we have to expand it, right? We know what is the seed points. Now we have to expand until we find the boundary of the cell, of the algae. That would decide the size, differential size. Now if I use absolute intensity, again it uses very nominal criteria of the global histogram around this pixel. But if I use a local contrast, then it uses the locally, what is the contrast between the cell and the background, because every cell has a different background here. So if you go for the locally, if I want to expand from every seed points, how do I expand? Depending on the local intensity for global, or considering the local contrast, meaning that if I have the window of a local contrast here, I know, okay, this is a maxima and this is the background, and accordingly the intensity will be decided, thresholding intensity of expanding, and it does it locally for every spots. I think it makes more sense in this. Yeah, exactly. Yeah, and this is a local contrast because it's a local window, right? Text. Okay, go next. Okay, now what is this? This is a slice basically, right? And it is giving us this information, region threshold, meaning that I have to select a region under which this cell should grow within that region. Okay, like if you clearly see now, if I switch off this, everything is switch off, but if you go here and say center point and change it to, let's say, 10. I can't change the color. Well, can I? Yes. Can you see that? Visualize the center points now. Okay, good. I go back to create now, and I want to, you see what happens if I go the more and more. So what will happen now here? It will just grow like this within that region. So I'm restricting my region of interest under which it should grow. So I would select here, right? But you should check that for every time point. I think as long as we have this white envelope around that point, then it's fine. Is it clear? And then I have two options, like from which I have to get the diameter. Either I have to take a region volume or the region border. Again, it is a bit complex that how do you want to make a boundary between the two, right? Maybe is it like a nearest boundary, or you have to take the volume into consideration, right? So let's not go into detail of that, right? Okay, always select the region volume. Majority of the time this would work. Okay, region border is that the border will be decided based on the nearest border of the cell. Okay, just go for the region volume. See the effect now, because we won't be able to see until we go to the sphere. Now you see that I think majority of them actually they are the same volume. Well, little bit of the change. I mean, this looks smaller, this looks bigger, right? You see that you can see it from if you go to 1.5. I think it looks smaller and this is bigger than this one. If you want to see it, then you should go to Statistics tab and then go to Detailed and go to Area. You see there is a variation in the area, and if you click here, it will sort this data set. So let's go for the maximum, the biggest one. So again, I don't need this. Go to Fit, Reset, and if I click here, the one which is selected will be highlighted as a yellow. You see this is bigger now. Got it? And you can select actually multiple like this. You see these are the things. Yeah. Deselect this now. Okay. We did one mistake because our whole aim here was basically to track the algae, and we did not switch on the track spots. So we don't have to delete this. What we can do is we can rebuild this algorithm, because we do not want to again remember and set the parameters. So what we'll do, we'll just click here go to the second tab, rebuild algorithm, say rebuild, and rebuild I would say okay, track spot over time. Yeah, it keeps all other settings, but I have an option of clicking on this one, green one, but that will also do the default setting of tracking, which I do not want. I want to till the spot creation, right? Still the spot creation. So I have to go one by one then. But it remembers all the settings that we have created here. Yes, yeah, exactly. Yes. Here, as I said, the sixth step of this entire wizard, you have a possibility of deleting some surfaces. As I said before, also you can do that, right? Deleting the manual deletion. So you can go and say, okay, I do not want this, so just delete. Okay, I'm not going to do that now because I'm happy with all this creation. Okay, so go next. Here is the point. So from here, the tracking algorithm will start. See, tracking is not automatic, right? Computer needs to know which one should be tracked to what. So if I go here, I have a couple of options here. First option is a Brownian motion. The Brownian motion, as you know, the Brownian motion, it's like a stochastic movement, a random movement of the cells, like a Polengren experiment, you must be knowing. Then second was the autoregression motion. What is autoregression? Autoregression is like a bit smarter way of estimating what is the likelihood that if the cell last two time point, if the cell was here, another time point cell was here, what is the likelihood that the third time point the cell would be here or it would be here? Okay, so for example, autoregressive works like this. So imagine that you have this cell here. This is T0. The cell is here, T1, and the cell cannot be here, right? The most probable or likelihood that the cell would be here is here, right? This position. That's called as autoregressive. So it basically considers what was its previous path. Based on that, it predicts this the future path. That's called as autoregression. Okay. So I think the majority of the time you have to select this autoregression. So forget about this explanation, but autoregression. Autoregression motion, yes. So autoregression motion expert, again I have to come back to my analogy. Let's say you have one time point here, and the third time point is here. That's autoregression. But maybe there are multiple such instances, right? It's not favorable for you, or it's not, biology is very complex, right? It's not very straightforward like a collinear time points. Maybe the two time points are here, very good, but the third time point there is a multiple option in the same, let's say, cone. There are two options here. How would I choose between these two? Yes, I will come back to that one, but maybe maybe I want to decide between these two guys based on intensity information, right? I want to know the intensity of the previous two time points, consecutive time points. There was some intensity, and what was the variation of intensity? The variation of intensity was less than 0.05% of intensity, and if I get these two guys, I will calculate what is the change of intensity. What is the change of intensity? If the change of intensity is predefined by the autoregressive, which is basically it's here, intensity weight. If it is within this range, consider that guy as a strong contender for connecting the track. Got it? Okay. But majority of the time, you first start with the autoregressive motion, because all these are very computationally expensive. So you have to be very careful while selecting. So I would always start with autoregressive motion. And if you're not happy, if you have too many multiply, they're very close together, then I think go for the outermost motion. Okay, but once we have done this algorithm, there are two parameters for algorithms. There are multiple parameters, but I think for the user there are two parameters. As you rightly said, that what is the maximum gap size? So there are two concepts: maximum distance, maximum gap size. What is maximum distance? Maximum distance is a distance that the particle from, let's say, one time point displaces or moves to the other time point. Got it? So let's say my t0, I'm here, and t1, it's here. But this is just the one event, right? Because we know that there are multiple cells, so that there are multiple consecutive sequences also. So we have to find the such consecutive event where there is a maximum distance between the two events. Right? It's basically the maximum distance traveled by the cell from one time point to the next time point. That's it in the entire data set. How do you find that? We need a distance calculation, right? And now it's not possible here, because how do I calculate, right? How it moves. So what should I do? There is a trick here. You click on this frame and decrease the size of the grid, the distance within the grid. Line width, increase the line width. Can you see this? The distance between the two grids? Yeah? And I think I would reduce a little bit. Yeah. What is the distance between the two grids? That I can control from here. You see? I increase. That's in my hand. That's just a visualization. I would go for, let's say, 10. And then I would just select randomly one event at this time point here, and I just go next to see what is the displacement this guy has. Well, it's not even, I would say it's just 2 or 3 micrometer, because the distance between the two. You understanding my point? Yeah. But this cannot be a case, because we're looking for the maximum displacement. So we have to see what is the maximum displacement that the cell can have, or the algae can have one time point. We have to see the maximum transition. If you just see it, just let me know. It is difficult, but let's see, for example, this guy over here. See? So I would say doesn't matter what you have, because if I decrease this 5 micrometer now, they are within the 5 micrometer, right? See? And maybe you can change this to some center point so that it's visible, right? What is the displacement that the cell can have? Well, 5 micrometer, okay? But just for the conservative purpose, I would increase a little bit, and this is what algorithm has done automatically. But not majority of the time this is the right option. You have to do this calculation by yourself, and the way you do it, like this one. Okay, what is the maximum gap size? The maximum gap size is nothing but the time point. How many time points you want to consider, and you want to allow the track to be continue even if there is no cell detected. Confused, I know. Imagine, so we have segmented the cells for every time point. In reality, it is not always sure, or it is not always necessary that you have a segmentation for every time point. Okay, you maybe set some algorithm settings in such a way that you are getting very nice segmentation for certain time points, and there are certain time points the cells are behaving something bad and you're not getting a segmentation. Okay, so I am here, I have segmented. This is T0, T1, T2, T3, there is nothing. And suddenly at T4, there is this cell comes up again. Okay, you know, I know, because this cell is the same lineage, right? But how would computer know that it has to keep on looking for the track and should not close the track here? So what should be the gaps as the size, gap size, meaning the time points? How many time points the computer should keep on continuing even if there is no event in between? Got it? So that's basically, if it is 3, meaning that it will leave the third 3 time points. Even if there is no, even if there is no next body which is connected here, it will still look until it finishes the 3 time points. If it finds at the 4th, connected. If it doesn't find at 4th, then just discontinue here, right there. Okay, but there is again a fourth option. The fourth option is, as we discussed, that this is the case where there is no detection of the cell in between this thing. So it can directly connect actually from this time point to this time point here. But actually in reality, we are interested in the time profile, right? Continuous time profile, some intensity values. So when you say click on this one, say fill gaps with all detected object, meaning that it tries to find some kind of maximas automatically, even if it wasn't there before, but because we know, because the computer knows now this has to be connected here, it tries to find some maximas, some intensity blob in between these two in this path of the track, right? So we are all doing this if there is a discontinuity in the track, because what if you have a discontinuity in the track, then you have to come and manually connect, generate the spots. But this is something you can do it automatically here. For the duration of not having the spots, but if the track is continuous, it will create some spots if the intensity is there. Okay, if it is not there, it will not create. In that case, yes, I completely agree with that. So if you have a like oscillation stuff, then it is not possible, right? Because how would computer know that yeah, the location, yeah. Yeah, because I mean Imaris is basically smart, but it is not it will not it's like a superhuman, right? How would computer know that yeah, it can generate some kind of a region if there is a local maxima. If there is no local maxima, it is okay for you, because then it will just connect let's say it's a peak and there's a crest trough here, right? And there is a peak here. It will just connect this here. At T0, sorry, this is T1, this is T0 and this T1. T1, what will be the value of intensity if you plot on the XY? It was 0, right? By default. So it will go down. So then you come to know, okay, this is oscillation basically. It's the same thing. It's just that it will not give you some kind of a random value. It will just give you, okay, data no not available kind of. Got it? Multiple layers meaning Z layer? No. Yeah. You have to do it individually. You can't do it like simultaneously. Yeah, but there's possibility of doing this. Oh, you mean the relationship? Yeah. For that, you have to use a cell module. Okay. Because in the cell module, everything is related to the parent object. The cell, then there's a nucleus, then there's vesicles. That is possible. Yeah. But even if you do not have a cell model, there is a possibility, because you can always generate a mask. Okay, I think I have to look for the masking, and then at that time I will tell you about this one. Okay. Tracking with a Z stack. No, I think the object will be, so that will be a 3D, is it? Oh yeah, it moves across. Yes, yes, yes. This is I'm talking right now. The example is 2D, but it will work for 3D, and not only XY, but XYZ. It can go anywhere. And autoregressive works exactly in the same way. Doesn't matter which, as long as it's a line in 3D. Okay. So I would say fill gaps. Go next. It depends, right? If you want, the only reason where you will switch on this tab, if you are very sure that there is no case, as she discussed, that if you know a priori there is a blank, then how would computer, right? But if you know that it is because of our setting that the setting was not optimal, then I think it's a good idea to switch on, because you know that there must be somewhere in that territory some maximas, right? Kind of. Yes. Okay. So now the track has been generated now. Okay, we have finally. But as usual, we have the classify tracks option. So we can also classify as like we filtered surfaces, spots. We can also classify based on track duration, like how long is the track. That's by default. But likewise, you can have the other options, like many options, like speed, intensity, all many options. So if I go for this one here, these are all the longest track basically. All the short track has been, yeah, deleted now. And this is the track, you see? Okay, so I'll go for this one, maybe up until this point or this point. Hit on this one. Done. Your tracking has been generated now. But I think this doesn't look good, right? I think we want some kind of a nice visualization. So let's change it to sphere and reduce the width of the sphere, so diameter. And here, I do not want to display at one time point all the territory, all the trajectory of the cell, but I want only just 2-3 time points, previous time points to be displayed only. So that is called as a drag and tail. It's like a tail basically, like, and how much long your tail should be, that will be decided by here, right? So if you are at here, just go. See, this is a tail, and that's basically going to. Okay. You can also calculate displacement, meaning that from t0, from initial time point to last time point, what is the displacement? This is displacement. Okay. You can also see it from here. So it starts here. I'm looking at here. It starts here, goes here, and ends up here. Okay. Yeah, you get all information. I'll come to that point. Okay. But this is just for visualization. I think I'll switch off this. Okay. You can go to statistics tab again, as I said, and just know how many overall. So number of spots per time point. So basically at this time point there are 20 spots. Number of tracks, 28 tracks. Maybe there are some false tracks kind of, yeah, or discontinuous tracks. Yeah, but this is the overall information. If you go to detail tab, area, it's the same because no, I think did we use different spot size? Yes, we did use different spot size. Yeah. We can also go for every. So this is an information, intensity, and for every time point, this number is changing. You see. Selection, the same thing will work. But this is not interesting. I think I want to see the profile of individual guys, right? Over time, the intensity. But before that, I want to come to the very important point, and that you might have to use a lot of the time. You might have to spend a lot of time on this, which is called as a track editing. Because this is a very beautiful example, simple example. It works very good. But majority of the time, this will not work. And for that, you have to come back and you have to change the track, edit the track. And I think it's very important that you should know that, how to do this. So let's look for the condition where you're not happy with. You think that it should have been done the different ways. Yeah, for example, this thing here. Look what happens. So the cells are coming here, good, good, and they touch together, and then just divides, right? So for example, if this cell here, imagine that you found later on that this cell's actually traject here and this cell goes there, which is not the case here, right? Because this cell continues, there's discontinuation here. Let's look at here and then try to edit this part. How to do that? Go to this tab, track, edit tracks. In edit track, it will show you all the tracks here. All the tracks. So to select that tracks, you go to the initial time point here. Here. We have to select this first, right? Go to the track subtab, track. Go to select mode, select, control, select, and go to object, sorry, so track, select, control, control. You see these yellow guys? They are the tracks which was selected. So select on this one. You select this one. See, the reason why I'm doing this, because I want to arrange the track now. I want to make sure that all initial tracks are the tracks that I want to edit. Otherwise, it will be very confusing, right? This is what it tells you. So you have an option of basically shifting this track in the very first, the very last. You can shift it to the left or right. You understand my point? Now this is a whole picture of the tracks. So yeah, exactly. Because right now we are going down, right? This is the time point. This is a time point, like that. So I'm arranging now this. I want this track to be at the very first, because it doesn't matter, right? Why? Because it is easy for me to basically then edit, right? Because I have to be only this section to work on. Otherwise, I have to just keep on going here and there. So that's why I'm saying this one. Now it has shifted here. Same thing, I want this to be shifted very next, right? Okay, I think we have selected a different one. So I wanted to show you the example and now I got confused. Okay, so where were we? We were here. So we want this to be edit, right? So select this one. Go to, this is always first, right? This is good. For this one, go on this one. So now it's next basically, right? Okay. Go next. Fine. What about this one? Go to the next there. This one. Exactly. I'll come to that point because I have to. I'm right now arranging all the first, which is necessary for addition. Okay. Do we have this? We already have that now. So we have everything at the left hand side now. Okay. You can zoom in like this. This one. Go to the time point where you want to start editing. Here. Right. So what is this track? This is the one. Okay. What is this? This one. So basically I want to connect this to this. Agree? But I cannot connect the tracks. You know, if I select this Control Shift key, I cannot connect the tracks. But for that, in order to connect the track, I have to just select the object. I have to be on object, select the last object of this track and the first object of this track with the control button. And then this connect will be activated. Just say connect. It has connected now. exactly. Yeah, yeah. Because we have selected that it fill the gaps, but it did not have find anything right there. That's why. Now you click here. This is my time point. I want to ensure if the next time point is accurate. And then the next one. Yeah, I think it's good. So for that you're yeah, so for that, because right now we are confused, right? What is what? So just say reorganize. So if you say reorganize, everything is reorganized, but there is no time point here, you see. But let's check if this is right. This one, this, and this. That's fine. Doesn't matter. Okay. Yes, it's all your choice, right? If you want to just get a statistics up until this point, that's fine. You just say click here, and just say disconnect. So this is disconnected now. Okay. Got it? Okay, let's see what happens next. Are we good here? We have to be on a track. I think it looks good now. Again, there is a problem here, you see. There is again one more problem, one more transition is coming with this guy. Got it? But now you know one, so you can do it many others also. That's fine for you? Okay. For the sake of time. And then let's say maybe you're interested only in these two guys. Only in these two tracks. Okay. So you select here to these two tracks. Go back to this one. And third tab and say duplicate. If you duplicate, look what happens. That's algae selection. Only these two tracks are selected. These two. And you can keep on working on this two track instead of many other tracks if you're interested in only these two tracks. So it has all the trajectories basically. Correct? And you can only go for this this statistics. So you have only statistics for these two tracks. That's it. So this is all about tracking. But maybe I'm interested, as I said before, that I'm interested in knowing the time profile, how the intensity changes over time, right? Or the shape changes over time. To look for that, there is a one option called as Vantage, which will give you the visualization of your data. So click on this. And once you click on this, this is also a wizard, okay, which has two steps. Here I'm creating a Vantage plot, which has an object algae. I want that, right, to display. It's fine. Then here you go next. And once you are in the next, it gives you all the options. So the category will be two. Okay. You have spot as an object and the track as an object, right? The information about the track, if you want to plot, there cannot be time axis. Agree? Because let's say intensity over the track, because track itself has a time information. But if you just have a spot, then you can plot intensity of spot over time, right? So you have a two category. That's why you have given this category. Either do you want only spots, then the time is activated. But if you say only track, then the time is not activated, right? Because there is no question of time in that track. You can only visualize the track. That's what it's showing here. It's only tracks. So maybe this is not interesting. For us, the interesting is this one. If you select on the spot mode, then you go to time, and then it displays the time point. But you can select what you want to display. Y-axis. You can select Y-axis here. So maybe let's say Y-axis of number 1. This is the intensity, the median intensity of all the tracks. And you can see it actually. Oh, this is how it's changing. and you can see it's a random, right? Nobody is different than the whole population because it's a just a random change of intensity. But if you, for example, if you are going for let's say cyclin B1 degradation kind of stuff, like the protein which is basically activated and fuses into the nucleus before the mitosis, that kind of things, you can see the curves and then goes down before mitosis likewise. So all this dynamic information, you can visualize it. What if the cells are dividing, if the cells are dividing just before that, there's a influx in the nucleus, right? And then suddenly the intensity drops down. So that kind of profile, you can see it. But that depends on your applications. Yeah. In the scatter plot, you can also see there are different options. So if you go for the last one, you can actually embed multiple information. So you have XYZ, that's my XYZ. So in the X, I can have real the position X, position Y, position Z. There is no Z in this case, right? It's just 2D information. You can have a scale as acceleration and the color as some other criteria, let's say intensity. So you can embed five dimension into your plot. This is for publication purpose. But again, you have to come to me, like you have to tell me, okay, what do you want to represent, and then I can give you the best suggestion, which plot is important. It's good, everything? Oh. Yes, that's the animation you're saying, right? Yeah, you're talking about animation. So if you just want to display this one, like you're talking about this one, like this, you just click on this record button here. This is recording. Yeah, it will give you all the options, you see. TIFF, AVI, MP4. Yeah, it's very easy. But okay, but if you want animation, meaning that okay, at certain time point you want to zoom in, and then do it like this, and then zoom out. That is an animation part. That is simple. I think I would advise you that once you have all your analysis done and everything done and it's a publication phase, just call me. I'll give you a suggestion about what should be the visualization and animation. Otherwise, it's very simple, right? You just go to animation. You know that, right? So just like, for example, here in this case, you go to animation here, animation tab, go to fit, zoom. I switch off this frame now. I do not want this frame to be displayed. And I want to, let's go to custom or just 360 degree. Here it doesn't make sense because it's 2D data. And then you see this is basically how the animation would look like. You see it's changing now. And it's also goes this way. Okay. Right. Like this kind of animation. You can also switch on the time points also. Okay. Right. So we just have 15 minutes left, I guess, right? Isn't it? No. 25. Okay, good. We are good in time. Any question about the tracking now? Start. Should we try with this? Yeah, looks very interesting actually. So that should not crash. Okay, here let's create a surface now and track surface over time. Nuclei I want to select. Let's go for the simple absolute intensity. Good. Check if I'm doing very good. I think it's good. Okay, go next. Number of voxels above, I don't care now. Well, I should delete this because we know that there was a problem, right? Go next, go next, and here. There is one more option called as a connected component, but a lineage. Because we know now that the cells are dividing and there are two daughter cells for one parent. If you use autoregressive, it will only track one of the daughter. But if you want the two daughter, like a lineage, then there is an algorithm. Go for this. So let's go for lineage now here. This parameter I don't have to explain. You have to fit accordingly. Maximum distance and the maximum gap size. Next. See what happens. Okay. Okay. Let's finish this and see what happens now. It crashed. Okay. But the point is you'd be seeing this one track and then there is division, like this continuation. Yeah, just visualize. Yes, like a number of generations, right? Number of divisions. Yeah, all this statistical information. You just come to me and then I'll explain you what information do you want. But there is all possibility of doing this. How many generations are there? What is the time? What is the duration of the previous division or the first division or the last divisions? Like all kind of information you can extract. What is the length of division? Kind of. What was the acceleration before division and things like that. What is the mitotic index, for example? Yeah. Okay. Should we go for a colloq or do you want me to tell you how to generate the surface? I think we still have time, right? I think I'll just show you how you can make your own surfaces, manual surface editing. Okay, let's go for the simple one, not to get crash. This one. Okay, so it's very simple that I can actually do this manual segmentation, automatic segmentation for nuclei. But what if we cannot? Then if you see the Z slice, this is how the nuclei look like. Okay, 3D. I would create surface for that. I have to create surface. I would say it's nuclei. And here I would say skip automatic creation. Skip it. Okay. And maybe switch off this. We do not need this. Here it will go to the third tab, which is basically creating object manually. Third tab here. Cursor intersects with what? So you have to select how do you want to, because once you click here, how do you want computer to interact your cursor? Meaning that in this case, and most of the time, it should be the channel on which you want to draw. It's basically this one. Yeah. And there are two algorithms for this, of drawing and of creating the surface in one go. One is marching cubes and another one is a magic wand. Okay. Now again, I don't want to spend time on explaining what these are. It's very fancy mathematical shape morphology creation. But what this magic cubes does is, first you have to go to select mode. Once you're in select mode, this cube will be generated. And the size of the cube can be changed through the scroll bar. And if you select the So the segmentation will be done automatically within this cube, but considering that channel, it won't create necessarily spots for the black pixels, for example. So if I zoom in and if I change to this box, you have to select this box in such a way that it accommodates the entire cell, like this. Maybe I zoom out. Is that fine? Just click there and press shift key, shift and click. Wow, generate. Okay, that's automatic creation. That's algorithm. So what it does is it tries to find within this region of interest window, tries to find the maxima local contrast basically, yeah, and accordingly it generates a surface. So if you are happy with this, fine, we have generated the surface now. That's it. You click outside, you have got surface. You can change the color whatever you want, but you can also extract all the parameters that you have that you can do it after automatic creation. Okay, let's look for what if I'm not happy with this one. Just click again, go to this tab now and say delete. That's gone. Go to the third tab and now let's say magic wand. In magic wand, what you do is, it's very interesting. It doesn't matter how much you select. You just have to click on certain a certain point within the object, and it automatically grows considering the intensities. You will see the effect now. So again the same thing, shift, I'm just putting it here, click. This is generated. No, size doesn't matter, but the problem here is, see, there is it only finds a connected component from this one. This is the ISO intensity curves basically. So again it depends. Like for example, nuclide doesn't make sense to use the magic wand because we know the DNA is not continuous everywhere, right? It has some lot of, yeah. Like for example here you see. So this is not a good idea. Good idea is to have a marching cube. But for example, cells where there is a continuous of intensity, continuum of intensity, then you can just use magic wand. Yeah. Let's see. Okay, yeah, set what else I can. Okay, this is all about selecting a point and then creating a surface automatically, right? But what if you have, let's say, pancreas or maybe a gut, which is very random in shape? It's not possible to segment, right? Because then is it possible to draw a pane and then just cut it and segment it like this? So that's what I'm going to do now. Just say delete surface, skip automatic creation, and instead of adding and deletion of the points, you can go for contour. To subtype contour. In the contour, in the board, you have to select on which axis you want to draw. Obvious choice is XY, right? Majority of the time. Okay, it's XY. Visibility, do you want to, okay, I'll tell you first how I'm going to do this. So in order to do this contour, I have to draw a contour for Z slices. And then if there is this contour here, this Z, say this is Z, okay, I'm drawing it here. There is a contour here, there is a contour here. Computer tries to find a surface which basically matches this contour. This is how it's going to surface. The point here is that you don't have to create contour for every Z point. You can interpolate, right? You just have to go for first, some 10, and then it gives an approximation. Otherwise, it's very hard, right? XY, and this is what that visibility is. That you want to visualize all the slices that you going to draw, or you just want to visualize only the next one, or just none. That's what it is. Let's go for all. Then this one, that's the slice position. You see here. You switch off this so that you can see all the slices here. So let's start from here. Then say draw. But before you draw, again there are some modes are there by which you can. So mode, you have ability of just drawing, just like tuck 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 dots. But imagine if you want to do this like multiple times, your finger will crash. You can do it by time. So meaning that for every 300 milliseconds, it will create automatically the contour. You just move this cursor and every time once. You can set that as a distance also. So every 1.1 micrometer, no matter you go, but every at that distance there will be a continuation of the curve. You can also have the roundish, basically how many surfaces, and like automatic, or this is called ISO surface, but I think this won't work. For that it has to have a very nice ISO curves, ISO line basically. But majority of the time you have to work on this one. Let's say time point. Let's go for time, 300 milliseconds. And I say now go to select mode and say draw. See what happens. So every 300 milliseconds, no matter what I do, I don't have to click it. I just have to move my cursor. You see, I'm not clicking it. Now it's done. Okay. We have to do that. We have to do that because it won't stop until we do that. It will keep on growing, right? Because for the curve, it has to be close. Then just roughly go to the next one here. Do the same. It highlights actually once you click on the end one. Go next. See, I'm not going to the next one, just roughly the couple of, I'm doing mistake here, but that's fine. Okay, and just say create surface. Let's see what happens. That's it. It has created a surface. I don't know how good that surface is, but let's see. I think it's good. Yeah. So if you switch off now, switch on the volume, and here, why is it displaying like this? Okay. Yes, because you're still in that mode, right? That's why. But not bad, right? But you see, it's not as good as automatic. There's a lot of this is approximation. That's a interpolation effect. But still, it's good. If you're not able to segment it somehow, right, because of some intensity variations and all, but you can do that like this. And the same thing, you can then go to the statistics tab and extract all the parameters that you want. Okay. There is also possibility of doing, let's say, automatic creation. Here, skip this, and you can go to auto fit. In auto fit, you can just go there and draw I don't know, just say just this, and then it basically auto fits. You just roughly have to draw a curve and then it adjusts according to the intensities. It's again fancy way of doing it, but I think again it will crash, so be careful. Just use the least resources from Imaris. I mean, this is good because if it's just 2D data, right, I would have just one sample, but you got the idea, right, how to do this, right? Let's go the final phase, which is the colocalization. For colocalization, I don't have data because I'm just skeptical now. Should I use this big data that I wanted to? But just for understanding of colocalization, we will use this plant cell because it worked before, right? It didn't crash that time. I know this is not an application for colocalization, but imagine that you want to colocalize, you want to find a colocalization between the chloroplast and the cell wall. I know it's very weird biologically, but imagine and apply the same rule for the other two channels that you want to colocalize, a 2 protein, for example. So for that, you just import this data set here, and there is this tab called as a colloc tab. Click on colloc. Okay. Once you click on the colloc, it will ask you on which channel you want to find the colocalization. So of course channel 1 you can select. If there are multiple channels, select this one, and this 2D histogram will show you roughly, without even doing all the fancy calculation, just by looking at this 2D histogram, you'll come to know whether or not you have a positive correlation or negative correlation. So just by looking at this, but it comes with the experience, right? I mean, also you can see now, because we know the biological condition of the sample, it has to be a negative correlation, right? Because where there is a cell, there is no cell wall, there is a cell wall, there is no cell, right? So, and you can also see it from this one. If this had been a positive correlation, you would not see this kind of this one. It's not this one, but it would be like this in the diagonal fashion, diagonal here, linear. This region, right? Okay, but nevertheless, so this is one, and you can actually see now the colocalization. Again, I don't know if you know the theory of colocalization, but the colocalization, there are different algorithms for colocalization, and in order to calculate the accurate colocalization, it is important to remove the background pixels from both the channels. Because if you include background, like for example in this case, this channel has this background and this channel also has this background. What is correlation? Correlation is if zero, whenever there is a zero, if there is a zero, then there is positive correlation, right? So if I include background now, all images will be positively correlated because it's all background. Majority of the pixels are background, right? And they are all 0, 0. So it is important to have the threshold for every channel. That, for example, in this case, for example, in chloroplast, I would only select the channel, the threshold, in such a way that I include the chloroplast cell here. I include this threshold for the cell wall in such a way that I include only the cell wall. Like, for example, this one. So that I know, okay, I have actually taken that into consideration. But you do it, this thresholding, I do it, or you do it. We have a different results. So there was a paper published by Costes in I think 2004 or 2005. He came up with an idea about automatic thresholding for colocalization. Okay. So then Imaris, there is an option of saying calculate threshold automatically using Costes. So if you click on this one here, calculate threshold, you accept that a p-value, it calculates the threshold automatically. And you see the threshold, it's 1 and it's 2. So according to this algorithm, all the pixels or voxels which are above 1 in the red channel should be considered for colocalization. Calculate threshold, kind of this question, you say yes. Do you want? Yeah, this is basically, this is again according to you have to read the paper by Costes. Okay, he has done a lot of simulations, and the way this Costes algorithm works is, so just say it starts from here, threshold. It goes until it finds that there is a negative correlation and sudden negative correlation. Okay, there is algorithm. In fact, I don't know where you there that time, but I think it was 1 year ago. I have conducted exclusive workshop on co-localization where I explained all the methods, all the principle behind this automatic calculation. So I have this presentation. So just send me an email. I'll send you that PowerPoint or the PDF where I have explained everything. Okay, Costas algorithm, and there are different ways of how to interpret the co-localization results. So just send me an email about this. Okay, but for the sake of time, this is how it does. Basically, it goes from here, 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 until it goes here, and then it satisfies. Now, okay, this is how you have to do, and it goes here 1 and 2. That's all. Once you know that, okay, this is the threshold that you should look for, you can go to this tab now. This is the very informative for you guys. So if you all this information, like a number of co-localized voxels, they are this much, percentage of co-localized volume, this much. But what is interesting the most is this one, the Pearson's coefficient in co-localized volume. Okay, and if you see this value, that is around 0.43. What is that value? Again, I explained in the workshop. Okay, but the Pearson's correlation coefficient can go from -1 to +1. -1 stands for negative correlation, very strong negative correlation. +1, very strong positive correlation. 0 means there is no correlation. Okay, and 0.43, I would say it's a positive correlation, but it is not strong correlation, because if you square this number, it gives you number which is less. So maybe if you square 0.4, whatever the number you get, that percentage would be explained by one of the parameter, meaning that, so ideally, if I changes according to you and you changes according to me, if I am 100% dependent on you, then I think we are strongly correlated. That's what the correlation meaning is. In this case, it's a 43. That's a 0.43 is a correlation coefficient. But if you square it, that's a standard deviation, meaning that the change in one data set is explained by that much square by the other one, and it is because it's a 0.43. If you square it, it's again less, right? So let's say around 0.2, for example. Okay, then only the 20% of variation off channel, red channel, is explained by green channel. 80% uncertain. How do you call this co-localization? I would say no co-localization, right? So if this number is above 0.8, then it comes around 0.60. So I would say at least more than 50% of variation of one channel is explained by others. So I would say they are co-localized. Okay. Z also. No. This is for entire. It's automatic. It's for entire data set. Okay, because it does by voxel, right? So in the voxel, it's a 3D. Then voxel. It doesn't matter. It's a. So this threshold is not calculated for every Z slice. Imagine the histogram for every voxel, meaning that if this is a cube, okay, this is a cube, all the voxels, it takes the intensity of that and plots it here. So it's a 2D histogram of a 3D object. Okay, good. There is also possibility of doing the co-localization, but within the region of interest. So that you can click on this one, mask dataset, and you say, okay, right now it doesn't make sense because we have to have the third channel for that. But imagine you have a nuclei, DAPI, and within DAPI we have a nuclei marker, BP1, foci, H2 gamma, H2X, and all, and you want to know if whether or not they within the nucleus only they are co-localized or not. In that case, you would select DAPI as a mask here and then segment it. So let's select now the chloroplast cell. So I'm interested in knowing within chloroplast what is the colocalization of chloroplast and the cell wall, which is very weird actually, but just imagine. No, within the chloroplast cell only, but right now the before what we did is overall channels, no matter if, yeah, you understand, there is no object information, but right now we are creating a mask, and within that only we are creating you see the histogram has changed now, and you see the value now. Let's see what is the value. You see negative, you got it now. Why? It's very straightforward why it is negative, and that's it. uh, this is the information basically you want at the end of the day. And you can say build colloc channel, this one. So if you say build colloc channel, the channel will be created with the colocalization information, and you can export that information. Exactly. So if you now you're here, then if you go to edit and image properties, and if you go to third one, this is the information that you have. You see it's negative, and you can export it now to whatever you want. The one thing you understood colocalization, yeah. But just call me. I know it's not that simple. Whenever you're working with colocalization. By the way, in Imaris you can actually work the other way around. You can click on the image itself, you see, and just ask, okay, I'm interested only the colocalization of this guy or this region of interest. You see, it only shows that information. You got it right. Okay, now it's completely weird, right? This data set is not for colocalization. Okay, one thing I didn't tell you is oh, not arena, how to export actually the information. Okay, so switch off this. Let's say you have done some kind of a surface creation. Should we do it for this one, or I'm a bit skeptical. Let's go for this one. Quickly create surface for I just wanted to show you once you do everything, how to export, but that's what we want, right? For the statistics. So maybe I think I just we should just spend I think 5 minutes. Oh, we already over time. Just 5 minutes for how to organize the data set in the arena. Okay, once you have so many, because that's the only last segment that is remain. So if you're in arena now, you can click on assay. This is how I've created now all my data set here. So if I say assay now here, I say, okay, today's data set or today's data set or something like that. Just say okay. The folder is created, and within that I can make a groups basically. So I would say, okay, knockout and wild type. Likewise, within that, just double click, go to image here. I can import the entire image folder, or I can import many images. This one. So if I go for images now, I can. Yeah, exactly. Yes, yeah. No, process it. I said in the beginning, right? You always should convert from raw to Imaris file format. So all this Imaris file format, you should go that location and get that data. Okay. So in this case, I would select this one for wild type. Imagine this is not wild type, but wild type, and then the other one, the knockout kind of, right? And you will see all these snapshots here, the thumbnails. I'm not going to do that, otherwise we'll crash again. But you have it there. Wait, I have actually one example here. The control like this, you see, okay, and the treatment like that. Okay, very important question that you didn't ask actually, is how to save the algorithm, right? I mean the rule set that you have written. For that I just need one example. Which one this time should we take? The simplest one is not working. Let's go for this one. Actually, this is working, which I'm surprised because this is a 3D data, right? I don't know why is it working so good. Let's go for the spots. Done. Okay. So once this is done, you can go to this statistics tab, and you see here now. So here you can export the one that you want to. So for example, now I am in area, and if I am only interested in area, which doesn't make sense here, but let's go for the intensity, whatever. Then I can export this only area information in CSV format, okay, or in XLS also, an XLS format. But if I want to import everything, because I don't know which features I will be using, so then you can extract this one. So it will export everything, all statistics value here, this tab. Okay. So second, yes, I'll come to that one. So, but this is like exporting the data. Okay. Now, if you want to work on top of this one, or you didn't finish, you are in between, just go to export, this tab, export as a IMS format always by default, and save on your local drive or network drive, whatever. It will always have all the information, data also, and the object that you have created. Okay. This store and store as, again, this is bit, yeah. So if you are using Arena, okay, when you say store, means that it will store into the Arena. It will not store the user specified location, but it will store in the Arena. So next time when you log in, you already have that there. You don't have to worry about where did you store, kind of. That's a good part of Arena, right? Everything is stored as a database. And store as meaning that within the Arena you can save it with a different name. That's a store as. Okay. Yes, one more thing. Let's say this is an algorithm. Okay, I have built an algorithm for the spot creation for the chloroplast cell. Let's say I have 100 such samples, and I want to apply the same algorithm for finding a chloroplast for 100 such samples. How do I do that? I have to save this algorithm. So I have to go to the second tab, store parameter for batch. Click here, just give name saying that spot creation for chloroplast cell, and click OK. If you say OK, then you can go to, let's say, I say today's batch, right? Today's batch or whatever, right? Spot, for example. Okay, say OK. And now if I go back to Arena, say no. What is this? You see, today's batch. And what happens is that if today's batch is here, right? If I click, let's say I'm opening now entirely different data set, but the plant cell. I opened it. I create the spot now. And here you go to today's batch. You just have to hit this green button now because you know everything is set. I will not do it, otherwise it will crash. But now I got it. I think that's it. Yeah, there is one more thing that that's basically in Arena. So basically you can make an experiment here. So you have a control and treatment now. So within the control I have 3 samples here. I have this algorithm of creation. So I would just right click, and there is no batch actually. Okay, I mean in the dance time it won't be batch. So you have to do it one by one, one by one, one by one to create like this. So here I have made a spot basically. You can go to object. So this is a spot that is created basically for this object. For this sample there is spot. This sample there is nothing, right? And for the previous one, which is the treatment, there is this one spot. Okay, now what if you want to compare this two conditions, control versus treatment? Then for that I have to create the collection. So I click on collection, I give some name, say control, which I already made it here. Okay, second time click and then go for the treatment, which I created here now. Yeah, so okay, you got this point. So you have selected, right? Okay, you have segmented everything. You go back again here. The reason why I'm creating this collection is that I'm going to drag and drop the spot object onto this collection for the treatment group. I'll show you what I mean. Exactly. Okay, let me do it beginning. I hope it works. I don't know, because okay, I can just try. Okay, collection, control, and treatment, control, object, spot. Just drag and drop. You see, I'm making a collection of all the control object, no matter from which sample they come from, because I want to just compare control versus treatment. Understand? Imagine this is your replicate. No, that algorithm is done. That's basically how you want to basically process multiple samples using that algorithm. Once you have done this, then I'm talking about now, because once you have processed this data, this will be created. You see, spot, you have processed this one, this is created. What is this? All this data belongs to control. Okay, see, in your experiment, ultimate aim is what? You have 3 replicates for control and wild type and knockout, right? Imagine these are the 3 wild type and this one is a 3 knockout. You have done segmentation and everything, and your aim is not to check if the one by one, but just overall, what is the statistics? Let's say size of the spots. Is the knockout different than the wild type? In that case, I'm talking about now. Okay. Yeah. So in the collection, what I'm doing is I want to store this 2 data in one place. This is what that place is. Yeah. So I'm in the control now. Here I'm clicking here. This is spots and just one. Same thing for the other one. Got it? Other thing, what I will do, I'll just go here, object, and here to treatment. Now just for the simplicity, I have just segmented only one. Here I did not have a segmentation for this one. Okay. Yeah, here the collection, you can see the spots. Yeah, but yeah, so this is not just to open, right? Because we already know from which data. This is to, I will tell you the output result and then it'll make more sense. Okay. So here basically we have created a one column which has all the data set from all the replicates from control. This is the treatment, which has all the replicate data from the treatment. Okay. Once you have done this, then you create, you go here in the workshop and you create plot as an object again, and then I'll come to this point and you say compare. I would say compare. Now in the compare plot, you have to tell, because compare can only accept this kind of data set. Now I got it. Okay, and then yeah, just drag and drop to this control compare. That's your control, that's your treatment. Now this compare has the information of these two guys. Okay, Just right click and say open in Vantage. Okay, it's just that maybe there's some, that data set is not available, the spot thing. Okay, but you will see all the fancy plots. You can go to 1D plot and see, okay, the distance between the size of the spots and objects and objects. Okay, makes sense? How was it? Useful? Good. uh, I think the only thing remains is this animation and the snapshot. You can always take a snapshot. Basically you just go to yeah, let's just open one of these. Yes, yeah, it's here. It's here, but there is no difference in the cell model and the what we discussed, because it was a time, right? Because I decided to have advanced, but always there was a lot of time with the basics. But this cell model is very simple, I mean, if you have time I can just show you. Just click on cell, right? And it gives you an option that how do you want to use the cell model. What is your options? Do you have a cytoplasm, nucleus and the vesicles in your channels, or do you have only cytoplasm and nucleus? Majority of the time we have that, right? Or you just have a vesicles and the cytoplasm, there is no nuclear marker. Or you just have just the cell, there is no nuclei. Especially in live cell, you have no nuclear marker, you just have a cell membrane, right? In this case you should use this one. And if you know that, okay, you have some cell membrane, but you have something with other channel information, some spot, then you should use this one. But the rest is same, because cell is created by surface and the spot is created by vesicle is created by spots. That's it. The algorithm is the same. The only good part of the cell is, as somebody asked me the first question, that how do I know that one track from the cell is the similar to this, the child track, right? This information is related now because cell is a one object here. So if there's vesicles, if there are many vesicles and if they have many tracks, but if the cell, if that surface is basically cell, then cell module knows that this tracks, vesicle tracks belongs to this main object or parent object, parent cell. That's the only thing. And then you can do additionally some information about the distance of vesicles from the nucleus, distance of the vesicles from the cell membrane, all this information, that's the additional part. Otherwise, it's the same algorithm. So for example, if I just go now, I think this is the best option for this one, this kind of data, right? Go next. See, it's asking nuclei. First is asking for nuclei. So go for this one. Forget about the nuclei now. See, it has created surface. Go next. See, cell is created now. Same thing, surface, the nuclei number, voxel, mean the size of the nuclei. So I wouldn't select this one because we know from our experience that at certain time point this actually breaks, right? That's why. Okay. Then go next, and it's asking me now to select the cell detection type. Is it a nuclei or is it like this cell boundary? It's a cell boundary, right? And then go for, but this is not actually a cell membrane, right? Because it's yeah, exactly, it's a cytoplasm. So I would go for this one then and select the green one. Smooth background subtraction. I think we should do a background correction and all. I would select this one. You see here, this is basically cell now, but because we haven't selected the advanced level, that's why it's very yeah, it's not that good. But and then go next. So it will expand from that seed point, that's a nuclei, and then it will expand until it gets the cell. I hope it doesn't crash. Got it? Okay, forget about the accuracy, but yeah, that's for one slice again. This is how it does basically, right? And then that's it, done. Okay, so it's because the graphics card issue, right? Because this cell module takes a lot of graphics. It needs a lot of heavy graphics card calculation. And because the laptop is also supporting this second screen and also recording, and that's why it's beyond its limitation. And they say, okay, it has been segmented, okay? It's just that it's not visualized. But you can see it, so there's a black spot over here. That's because of the some cell issue. Yeah, you see here? And then you can, if you click here, the statistics tab, you get all the cellular type information. Like what is the distance of nucleus from the membrane and what is this nucleus to cytoplasm ratios and stuff like that. But that you can anyways calculate by having a spot and surface. Yeah, but that's it. That's the only difference, the cell module. Yeah, good. Welcome.